But we have a lot to do in lecture 16 today. You can see in 16A and 16B the topics are quite numerous, but they're all pretty important topics, and some of it's review and some of it's new. In lecture A, we're doing geometric interpretations of continuous growth rates. We talked about the compound interest last time. I want to not do as detailed of an example, but show it more visually in a simpler example. Local linearity and good approximations of what does the word good mean, and then something called Newton's method, which is based on tangent lines. And then 16D, we'll go back to infinitesimal calculus, calculus without limits, applied to the derivatives of sine and cosine, like I did at the end of lecture B last time, and to something new called the product rule. Let's consider a really simple situation, and also a very unrealistic situation. Usually, consider an investment with a 100% annual rate of return. Okay? In other words, the interest rate is 100%. Of course, bank accounts never do that. And most other kinds of investments are not 100%. The only way you're possibly ever going to get a return of 100% is probably if you invest in stock of a brand new company that does really well right away. That's probably the only way you're going to get a 100% return. And even that is going to be variable over the course of many years. Okay? But just to keep things simple, this means the b for the exponential function is 2. And that also means the investment doubles every year. For example, suppose you invest $1,000 at time 0. The formula then is this. The initial way to write the formula is 1,000 times 2t is the simpler way to think about it, because you know the money is doubling every time. So when t is 1, for example, this is 1,000 times 2 to the first. 1,000 times 2 is 2,000. When t is 2, you get 1,000 times 2 squared. 1,000 times 4 is 4,000. When t is 3, you get 1,000 times 8. 8,000. Your money is doubling every year. That would be amazing. This can be written in terms of e. I said k is the natural log of b, right? Our old friend k. Shot here. Is natural log of b when you want to write it as e to the kt. Another thing you can do is you can write 2 as e to the natural log of 2. Kind of a strange thing to do, seemingly, but that's certainly okay, because e to the x and natural log of x are inverse functions. 2 does equal e to the natural log of 2. And then I can use a property of exponents to multiply those exponents like that, and then natural log of 2 is about 0.693, as we saw last time. So that's how to write the exact same function in terms of e. In other words, the continuous growth rate, the k in this case, is 69.3% per year. That is not contradicting the fact that your money is doubling. That is actually growing by 100%. Here's a graph to illustrate this. Okay? So this blue graph is the graph of the function, the amount in the account as a function of time. It's increasing in concave up, as all exponential growth functions are. And then you see I've got a couple tangent lines. I've got a red tangent line right here at t equals 0. And I've got a green tangent line right here at t equals 1. Remember, one of the things I wrote down last time, or I had on the PowerPoint, was what that thing equaled in the situation. I called this the instantaneous relative rate of growth. Instantaneous relative rate of growth. The word relative needs to be in there. Relative rate of growth. Meaning you want to think of it as a percentage. Or it can be thought of as a percentage. And for this problem, well, for the problem from last time, we saw that this actually equaled k. The continuous growth rate. And that helps us, and in this case, again, that's 0.693, about 69.3% per year. Remember that I said that represents the growth that would happen if the growth were linear instead of a concave up graph, instead of exponential. The blue graph goes up by 1,000. It doubles from 1,000 to 2,000 as t goes from 0 to 1. The red graph, that's the tangent line, does not double. It grows by 69.3%. And It went from 1,000 to 1,693 at time 1. F prime of 0 divided by f of 0 is equal to k, 69.3% here. It's the ratio, that ratio there is the length of this line segment, which you can think of as f prime of 0 times 1. The derivative times the change in t. Even symbol, the change in t is 1. It's the length of that line segment divided by the length of this line segment, because that length right there is the same as the function value of 0. And it works no matter what the time is, actually. You go from time 1 to time 2, an increase of 1 year. The money grows along the blue curve. It doubles from 2,000 to 4,000. Along the green tangent line, it doesn't double. It grows by 69.3% again. The length of this line segment right here divided by that line segment is still 69.3%, 0.693. And if you calculate f prime of 1 divided by f of 1, this distance right there is 1386. 3,386 minus 2,000. I'm looking at that one right there. Is 1,386. Divided by 2,000, which is the length of this line segment, which is the same as the function value of t equals 1. So to summarize again, what the continuous growth rate means is that it will give you the amount of growth if it followed a straight line rather than a curve, no matter what time you start at, t equals 0 or t equals 1. And what that means is that the ratio of this side of this triangle right here to this distance right there, which is the same as this, stays constant no matter where you are. This divided by this is 0.693. This divided by this is also 0.693. Okay? Again, take the time to check it after class. Just telling you what the K means. That's what this is emphasizing. Another subject. What does it mean for the tangent line approximation to be good? Remember, here's the tangent line approximation. L of x is this function. Actually, this L of x, I don't think I used that on the previous slides. What is L of x? L of x is a function whose graph is the tangent line to the graph of f at x equals a. Draw this on the board if you didn't catch this here. So f, who knows what that looks like? We're not talking about exponential growth here, necessarily. Say that's the graph of f of x. And say a is right here. This point then would be a comma f of a. The tangent line would look about like this. It's just kissing the graph at that one point. It's locally linear. If you zoom in, it's going to look more and more like the tangent line. It is okay for tangent lines to cross the graph in other places, by the way. That's not a problem. They don't do that for circles. Tangent lines for circles don't cross any other point. But tangent lines for function graphs can cross other places. This is the graph of the function I'm calling L. L for linear. It's a linear approximation. And it's essentially the slope point form, or point slope form of the equation of this line. Okay? F of a plus f prime of a times x minus a. This is like the y. This is like the y1, you might say. And a is like the x1. This is the slope in the point slope form of the equation of the line. These functions are close together when x is close to a. So L of x should be a good approximation for f of x when x is approximately equal to a. But what does it mean to be good? It means it's a good approximation if the error rapidly goes to 0 as x approaches a. What is error? Is it a mistake? The error doesn't mean mistake here. It means how far you are off from the true value by using the approximate value. F of x is the true value. L of x is the approximation. The error is the difference, f of x minus L of x. I'm calling that error of x instead of just error because it's really a function of x. These two things depend on x as well. In this picture here, come back over here, f of x minus L of x for any given x, like right here say, is this vertical distance there. Thought of as a positive distance because f of x is above L of x. If the picture had been more like this, then the tangent line would be above the graph. Then actually the output for f of x is below the graph, the output for L of x. And f of x minus L of x would be negative in that case, when the graph is below the tangent line. But this is just begging a question. What does rapidly mean? I'm trying to fix what good means by saying this, but what does rapidly mean? It's just pushing the ball down the road further here. It means what I'm about to show you, well, here's a short version. It means if you take the limit of the error divided by x minus a, that goes to 0. Why does that mean the error goes to 0 rapidly? Essentially, here's the intuition. The error goes to 0 so rapidly that this fraction goes to 0, which means even though the top and bottom are both going to 0, as x approaches a, the top's got to be going to 0 much faster than the bottom to make this limit go to 0. You see at the bottom, x minus a, that's going to 0 as x gets closer and closer to a. This is approaching 0. The error is approaching 0 as well. This fraction doesn't have to be approaching 0. If it's a bad approximation, the fraction probably would not be approaching 0. The fact that this equals 0 means this goes to 0 faster than this does, significantly faster. Here's the details for an example. Say f of x equals x squared and a equals 3. There's a lot of details there. Go ahead and write them down. I think it's probably good. I'll draw a picture as you write. Big picture of what's going on there is I'm trying to find the equation of the tangent line. Thinking of its graph as being the graph of some function that I'm calling L of x. So I'm using this formula with a equal to 3. I'll go ahead and plug 3 in there. So I got to evaluate f of 3. I got to evaluate f prime of 3. Plug those numbers into the formula for L of x. Function is x squared, a is 3. That point is the point 39. We've just found, if you look at those details there, the tangent line at a equals 3 it's got a slope of 6. That line has a slope equal to f prime of 3, which is 6. The error is f of x minus L of x. F of x is going up like this. L of x is this line. F of x is above L of x, so when I do the difference, it's going to be a positive quantity. This thing right here is what the error simplifies to. Does that go to 0 as x goes to 3? It does go to 0. It's continuous at 0. If you plug in x equals 3, you get 9 minus 18 plus 9 is 0. So it does go to 0. Does it go rapidly? You got to divide by x minus a, x minus 3 in this case, and see if that still goes to 0. It turns out for this example, this happens to be a perfect square. It's x minus 3 quantity squared. So when you simplify it, you just get x minus 3 as long as x is not 3. And that obviously goes to 0 as x approaches 3. This is alternative limit notation, by the way, when I write the arrows there. When I write limit as x goes to 3 of x minus 3 equals 0, that's equivalent to writing x minus 3 goes to 0 by an arrow as x goes to 3 using an arrow. Approaches is another word used. Here's a graphical way to interpret all this. Kind of a complicated graph, but we can reason it out here. The blue graph is the function, f of x equals x squared. The red graph is the tangent line at a equals 3. It's the graph of a function L of x, which is 6x minus 9 when you simplify it. The green graph, zoom in out if you need to here, is this parabola, because it's the graph of this quadratic right there, which is the same as x minus 3 quantity squared. Its vertex is at x equals 3. And when you do the division, x minus 3 squared divided by x minus 3, you get the orange graph. Technically not when x equals 3. Technically the orange graph has a hole in it at x equals 3. But its limit is certainly 0. Essentially the orange graph, well, is the green graph divided by the orange graph. In this case, the thing you divide by, x minus 3, is the same as what the orange graph equals when x is not equal to 3. This is going to 0 as x goes to 3. Just a graphical way of understanding what's going on there with the function. Not going to talk about error again for maybe another week or so. It does come back in section 3.9, I believe. We talk more about linear approximations and error in that section. I'm not going to assign any problems about this today, but I thought it was worth introducing. Kind of a hard idea. It takes a while to get used to. It's best thought about with examples and with graphs. The next slide is yet another topic, still related to tangent lines, and also related to your project. So this next slide has those characteristics. Okay, it's important partially because it's related to tangent lines, partially because it's related to your project, and partially just because it's a useful thing on its own. It's called Newton's method. Application of tangent lines. Here's a hypothetical situation. Suppose you're on a desert island. No, suppose, maybe you are on a desert island because you have no technology with you, and you're told you're going to die in 10 minutes unless you can approximate the square root of 20 to 3 decimal places. What would be the best method to save your life? We can make it more extreme and say 5 minutes. What's the best method to save your life here in this hypothetical situation? It's to use this thing called Newton's method, along with some arithmetic. Newton's method is a method for approximating roots of functions. Square root of 20 can be thought of as a root of a function. The function f of x equals x squared minus 20 is one example, the simplest example perhaps, of a function, one of whose roots is square root of 20. The other root would be negative square root of 20. We'd like to approximate that without technology. Here's the method. We'll go through the method once, maybe try to use it, and then we want to try to understand it as well. Estimating the root, not just of a continuous function, but also a differentiable function. The derivative of prime needs to exist everywhere near the root at least. The first step is make an initial good guess. Call it x0, x sub 0, or x naught for short. Sometimes physics profs especially tend to say x naught, naught meaning 0. I'll say x0 typically, or x sub 0 to avoid the confusion. The word naught is not the word not, but naught, N-A-U-G-H-T, effectively meaning 0. This is sometimes called a C, an initial condition, a guess, a good initial guess. For square root of 20, the answer's got to be between 4 and 5. So a good initial guess might be 4.5. Though I'm going to pick 5 for my initial guess, because it'll make the numbers work out a little bit more nicely and make the picture easier to see. Secondly, you use the following recursive formula, and step 2, really you do it over and over again. You iterate. Define some other numbers, x1, x2, x3, until you reach the accuracy you desire. I'm saying 3 decimal places, 3 places after the decimal. Newton's method usually works pretty well. It usually converges pretty rapidly to the answers. I'm going to just do a couple steps and see how close we are. Here's the formula. X sub n equals x sub n minus the quotient, x sub n minus 1, excuse me, x sub n minus 1 minus the quotient f of x sub n minus 1 divided by f prime of x sub n minus 1. So in other words, you need to understand how to think about this formula. Write this on the board here. x1 equals x0 minus f of x0 divided by f prime of x0. x2 equals x1 minus f of x1 divided by f prime of x1. x3 equals x2 minus f of x2 divided by f prime of x2, etc. This is called a recursive formula. It's something you use over and over and over again until you're just either tired of it or you get the accuracy that you want. The project is about iteration and Newton's method. Iteration in general, Newton's method is a special kind of iteration. And then we want to know why it works. And by the way, these arrows here are, again, should be dot, dot, dots. It's a problem going from my Mac to this PC. Those should be dot, dot, dots. We do want to understand why this works, but let's just use it first for this example. So we want to estimate the square root of 20. Let's see if how far I can get without a calculator. Let's use x0 to be 5. That's our initial guess. The function that this is a root of, again, is f of x equals x squared minus 20. So its derivative is 2x. The formula in this case simplifies to x sub n equals x sub n minus 1 minus f of x sub n minus 1 is this, and f prime of x sub n minus 1 is this. Realize when I write this here, this means x sub n minus 1 quantity squared. X sub n minus 1 is 1. So if x0 is 5, what is x1? Replace the n with 1. x1 will be x0, 1 minus 1 is 0, minus the fraction, that is x0 squared minus 20, divided by 2 times x0. 5 minus 5 squared minus 20 over 2 times 5. 5 minus 5 squared is 25, minus 20 is 5. 2 times 5 is 10. And that's pretty simple. 5 minus a half is 4.5, which is the other better initial guess that I mentioned. Let me write this as a fraction, 9/2. Let's try one more step and see if it's good to 3 decimal places or not. And then we'll cheat and use technology. What is x2? It's x1 minus the fraction x1 squared minus 20 divided by 2 times x1. 9/2 minus 9/2 squared minus 20 over 2 times 9/2. 9/2 minus 9/2 squared would be 81 over 4. 20 as a fraction over 4 would be 80 over 4. 2 times 9/2 is 9. That's 1/4 right there. 1/4 divided by 9 is going to be 1 over 36. get a common denominator of 36. Got to multiply the top and bottom by 18 here. 9 times 18 is 164. 62. Minus 1 over 36. 161 over 36. Now, if I truly did not have technology, does that look good? Double check that one there. Okay, I think that's good. If I don't have technology, I can figure out what this is as a decimal by doing some division like this. I don't want to do that. Let's now use technology to see what this is. 161 divided by 36. It's as an exact decimal, it's 4.472. It appears with the 2 repeating. So approximately to 3 decimal places, 4.472. You can try square root of 20 on your calculator. To 3 decimal places, you get 4.472. Amazing. Try it. Go ahead and try it right now if you got a calculator. Take the square root of 20. You get about 4.472. In just 2 steps, we got good to 3 decimal places. And if I had picked a better first guess, like 4.5 for my first guess, it would have only been 1 step, and I would have gotten it good to 3 decimal places. Do a few more steps, you're going to be good to like 10 decimal places. It converges really rapidly. But why does it work? It's related to tangent lines. The picture will help you see why it works pretty well. Use a tangent line equation and make pictures to see why. Okay, the tangent line to the graph of f at this point, notice I'm using an x0 here instead of an a because that's my seed, my initial condition. It's like an a. Is that equation right there? Right? That's point slope form again. Exact same equation that I had up earlier, top of the board, except an x0 instead of an a, and a y instead of an L of x. There's your initial output of the function when x is x0 times the derivative times x minus x0. The linearization. If x0 is right here, there's this tangent line. The tangent line has equation y equals f of x0 plus f prime of x0 times x minus x0. If you follow that tangent line down to the x-axis, it gets pretty close to the true root. The true root is right here. Question? Say it louder. X0 is just the initial point. It would equal xn minus 1 if n is 1. This is just a general formula. This is just a particular number I picked as my seed, my starting point. I want to find x1. What Newton's method is doing geometrically is it's finding the x-intercept of this tangent line and calling that x1. And then if you continue the process, go up, find the new tangent line and find where it intersects, you call that x2. And you can see from the picture it's getting pretty close to the true root of the function, which is right there. The x-intercept of this line is x1. How do you find an x-intercept? You know this. Usually you have numbers, right? No specific numbers here, but you know the principle. Set y equal to 0 and solve for x. You know that, okay? You can apply it. I set y equal to 0. Solve for x. I'm going ahead and calling it x1 because that's what it's going to be. I didn't have to call it x1. I just know that intercept is going to be what I'm labeling x1, so I'm going ahead and putting an x1 there. Solve this equation for x1. It's an abstract equation, but you can solve it. You got to isolate the x1. So you want to subtract this from both sides, then divide both sides by this, and then the third step would be to add x0 to both sides. Here's the steps. There's the subtraction step of f of x0 from both sides. Here's the division step, and also I switch the sides. And here's the last step, solving for x1. And lo and behold, you get the exact same formula as the recursive formula that I erased in general. This is like your xn, this is like your xn here. This is xn minus 1 minus f of xn minus 1 divided by f prime of xn minus 1. You might wonder, does it work the same way if I find x2? Yeah, it would be the exact same method, giving you the exact same formula, just with different symbols. You'd be solving for x2 in terms of x1. But it's the same method. Reiterate this stuff. Here's a picture of what really is going on. Here's the graph of x squared minus 20. Its x-intercept, its root is about 4.472 we saw. That point is x0, which is 5. Go up to the graph, find its x-intercept, that's called x1. If you zoom in closer, you can see x2, barely. Here's x0, go up to the graph, here's the tangent line. Its x-intercept is x1. Do it again, you can barely see another dot there, another dot there. That second dot is x2. This dot right here is x2. Almost to the root, as far as we can tell. Looks like it's pretty much right on top of the blue curve and the x-axis. It's not exactly at the root, but pretty close. Okay. Let's take our break.